We will now begin studying two new types of functions, the exponential and logarithmic functions, and we begin with the exponential function. Now recall that in linear growth, there is a constant rate of change. In exponential growth, however, the rate of change grows over time. A few that are commonly used for exponential growth are percent growth, and this refers to a change based on a percent of the original amount. Then I have exponential growth, which refers to an increase based on a constant multiplicative rate of change over equal increments of time. And then we have exponential decay, which refers to a decrease based on a constant multiplicative rate of change over equal increments of time. So a very common thought experiment for exponential growth is as follows. You are approached by a rich prince from a faraway nation. He says to you that he can give you $1 million today, or a penny doubled every day for the next 30 days. Which is the best option? Now, I want you to pause the video here and give this some serious thought. And when you have your answer, come back to the video. Now, it may be tempting to take the $1 million right up front. But let's just examine the second case and see what happens. So here's a table that shows the day and the amount that you would have. So on the first day, you have a penny. And remember, it doubles every day. So on the second day, you would have 2 pennies. Then you would have 4 pennies, 8 pennies, 16, so on and so forth. And if you notice, by the 30th day, you would have $5,368,709.12. So you'd have roughly $5.3 million if you went with this option. Now, granted, it's going to take a while for this option to be the better option, but it definitely is. By the end of the 30 days, you have 5.3 million as opposed to the 1 million up front. Right, so that is definitively the better option. Now, a closer examination shows that while the growth starts off slowly, it will really begin to take off after the 15th day if we go back and look. Right, so the 15th day we have $163, right, over 300, then over 600, over 1,000, 2,000. So at that point, it really begins to take off. This is the true power behind exponential growth. So the exponential function for any real number x, an exponential function is a function with the form f of x equals a times b to the x, where a is a non-zero real number, which is called the initial value, and b is a positive non-unitary real number called the base. And remember, unitary means 1, so this is saying that b is a positive real number not equal to 1. So this following table compares exponential growth to linear growth for several values of x. Right, you can see that for a while they're equal and the growth is as drastic, but then it will really start to take off, right? Like, look right here. After 6, 2 to the x is already 64, whereas 2x is 12. So some observations. Here's a graph of the function 2 to the x. From here we can see that the domain is all real numbers. The range is all positive real numbers. F of x goes to infinity as x goes to infinity. F of x goes to 0 as x goes to minus infinity. F of x is a strictly increasing function. The graph never touches the x-axis, which means that y equals 0 is a horizontal asymptote. And it has a y-intercept of 1. So if we consider the exponential function of the form f of x equals b to the x, b is greater than 0, b not equal to 1. And f of x will have the following characteristics. F of x is 1 to 1. Y equals 0 is the horizontal asymptote. The domain is all real numbers. And the range is all positive real numbers. It will never cross the x-axis. It crosses the y-axis at 0, 1. The function will be monotonic increasing, meaning strictly increasing if b is greater than 1. And it'll be monotonic decreasing if b is less than 1. So these properties hold no matter what value of b we have. The only ones that'll change based on the value of b are these last two. Increasing for values larger than 1 and decreasing for values less than 1. Well, this is the difference between growth and a decay. Growth is increasing. Decay is decreasing. So we have growth whenever b is greater than 1, and we have a decay whenever b is less than 1. So now to sketch the graph of an exponential function, first create a table of points. Second, plot at least 3 points from the table, including the y-intercept 0, 1. Third, draw a smooth curve through the points. And fourth, and this is completely optional, state that the domain is all real numbers, the range is to infinity, and the horizontal asymptote is y equals 0. I say this step is optional when I sketch graphs of exponential functions. In fact, in general, whenever I sketch a graph, I don't write down what the domain and range are. I also don't really write down the asymptotes. I just represent those with dashed lines. Well, we're going to go ahead and sketch the graph of an exponential function. This one is a decay function. We will sketch the graph of 0.25 to the x. Right, so this is an exponential decay function, which tells us that it's going to be monotonic increasing. Right, so first let's look at several points. So we already know that we're going to have the y-intercept to be at 0, 1. So I'll just go ahead and plot that point right now. All right, let's look at some other points. So if we take x to be negative 1, then f of x will be 0.25 to the negative 1, and I'm going to rewrite 0.25 as a quarter, right? So that I can say, well, f of x is 4. So that's going to be right up there, right about there. That looks good. Right? If f is 1, then f of x is a quarter. So quarter would probably be right about there. And now they say to sketch, what was it, 4 points? Plot at least 3 points. There's my 3 points, right? So now it's just connecting the dots with a smooth curve. All right, so there we go. That is a sketch of 0.25 to the x. So the number e is an irrational number. Specifically, It is the irrational number 1 plus 1 over n to the n as n goes to infinity. We typically take, as an approximation, e to be about 2.718282. So to truly understand this definition, you're going to need some calculus 1 knowledge. Specifically, you're going to need to know what a limit is. But for now, just understand that e is this number as n gets really, 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 really large. Now, e itself is used as the base for many real-world models. We call the function f of x equals e to the x the natural exponential function, and we say that e is the natural base. All right, we're going to continue studying properties. Basically, we're going to look at now all the transformations. So first, let's look at the translations. For any constant c and d, the function b to the x plus c plus d will shift the parent function b to the x vertically d units in the same direction of the sign of d. Right? So if d is positive, it shifts it upwards. If d is negative, it shifts it downwards. It shifts our function horizontally c units in the opposite direction of the sign of c. So if c is positive, shifts it to the left. If c is negative, shifts it to the right. The y-intercept becomes 0, comma b to the c plus d. The horizontal asymptote now becomes y equals d. The range becomes d to infinity. And the domain will still be all real numbers. Now let's look at the stretch and compression. So for any factor a greater than 0, the function a times b to the x stretches the parent function vertically by a factor of a if a is greater than 1. It will compress the parent function vertically by a factor of a if a is less than 1. It now has a y-intercept of 0a. Y equals 0 remains the horizontal asymptote. The range remains all positive real numbers. And the domain remains all real numbers. Now for any factor a greater than 0, the function b to the ax stretches the parent function horizontally by a factor of 1 over a if a is less than 1, compresses the parent function horizontally by a factor of 1 over a if a is greater than 1, has a y-intercept still at 0, 1, y equals 0 is still the horizontal asymptote, the range is still all positive real numbers, and the domain is still all real numbers. Finally, let's look at reflections. The function f of x equals a negative b to the x is a reflection of the parent function b to the x about the x-axis. It has y-intercept, now at 0, negative 1. Its range is now all negative real numbers. Its domain is still all real numbers. And y equals 0 is still the horizontal asymptote. Now the function b to the negative x is a reflection of the parent function about the y-axis still has y-intercept at 0, 1, still has range of all positive real numbers, still has gain as all real numbers, and still has y equals 0 as the horizontal asymptote. And this chart just summarizes the previous few slides. So write the equation of the function described below, then give the horizontal asymptote, domain, and the range. So f of x equals e to the x is vertically stretched by a factor of 2, reflected across the y-axis, and then shifted up 4 units. All right, so we know that we're starting with e to x. So it is vertically stretched by a factor of 2. So vertical says it's going to be outside of the function. Stretching says it's greater than 1. Factor of 2 tells me it's 2. So that's going to give me 2e to the x, and that takes care of the vertically stretched. It is now reflected across the y-axis. So this tells me that it's going to be now 2e to the minus x. And then shifted up 4 units. So that tells us that we will get 2e to the minus x and then plus 4. We've now taken care of all the transformations. So our new function, call it g of x, is equal to 2e to the minus x plus 4. The domain is still all real numbers. The range becomes 4 to infinity. And the horizontal asymptote is now at the line y equals 4. In 2013, the population of India was about 1.25 billion, with an annual growth rate of about 1.2%. We wish to model this as an exponential growth function p of t, where t is the number of years since 2013. Then we will use this model to estimate to the nearest 1,000 what the population of India will be in the year 2031. So our initial condition is 1.25 billion. After a year, it grows by 1.2%. So it's going to be 1.25 billion plus 12% of that. So this becomes, I'm sorry, it's not 12%, it's 1.2%. My apologies. So we get 1.012 times the initial condition, call it P naught. So that's what I'm going to do here. I'm going to replace this now with P naught, and I'll replace this here with P naught. After the second year, we have to take this one, which I'm going to call P1, and it's the same formula. So this is 1.012 times P1, but P1 was 1.012 P0. And so this becomes P0 times 1.012 squared, right? And so on and so on. So our model, which I'll write at the top, is P of t is equal to P0, which is 1.25 billion, times 1.012 to the t power, where t is the number of years after 2013, and P of t is measured in billions. We now need to use this model to determine, to the nearest thousand, the population of India in the year 2031. So I'm going to get rid of all this work down here. So in the year 2031, our t is going to be 2031 minus 2013, which is 18 years. So we want p of 18. So this will be 1.25 times 1.012 raised to the 18th power. This is approximately 1.549 385, and remember this is measured in billions. And this is rounded to the nearest thousand, right? This would be 1 bit, this would be million, 100 million, 10 million, million, 100,000, 10,000, 1,000. So this becomes 1,549,385,000. So if this model holds, and it's a constant increase of 1.2%, then in the year 2031, India's population will be about 1.5 billion. Well, now let's look at an extremely useful application of exponential growth. That's the concept of compound interest. So an example of compound interest is savings instruments, in which earnings are continuously reinvested, such as a mutual fund, the stock market, a savings account. In these types of accounts, interest is earned not only on the initial investment, but on the interest that was earned in the previous period. The interest earning on such an account per year is known as the annual percentage rate, the APR, or the annual percentage yield, the APY. So the annual percentage yield refers to investments such as mutual funds, where the interest you earn varies per period, right? So they just an average of the annual yield. So let's consider an initial investment of P0 in an account with an APR of R that compounds n times per year. So after the first compounding period, the account will have A1 is equal to P naught plus P naught times R over N, right? So it's our initial investment plus how much interest we gained, which is our annual percentage rate divided by the total number of compounds. Factor out the P naught, we're left with P naught times 1 plus R over N. So this is how much we have in the account after one compounding period. If we now look at the second compounding period, it would be A1 plus any interest earned, which is A1 times the APR divided by the number of compounding periods. But A1 is this up here. So if we substitute it in, we get P naught times 1 plus R squared. Well, after the third period, it would be the amount in the account plus the interest earned on that amount. But A2 is this right here, right? So plug that in, and we get P naught times 1 plus R over N all cubed. So in general, after the nth compounding period, the account will have a total of A equals P naught times 1 plus R over N to the nth power. So after T years, right, so this would be after 1 year. After T years, we just raise this whole thing, this part here, to the tth power. So it would be A equals P naught 1 plus R over N all to the nt. And so here is our compound interest formula, where A of t is the account value after t years, P naught is the starting amount of the account called the principal or the present value, R is the APR expressed as a decimal, and N is the number of compounding periods in 1 year. Now, while this formula can be used for investments, this formula can also be used on debt. Right? So if you take out a debt that has a certain interest rate per year, you can also use this formula to determine the new debt balance. And we don't want to talk about debt. So let's look at a positive example. The S&P 500 is known as the Standard & Poor's 500, which is just a collection of 500 of the largest companies in the United States. Over its lifetime, the S&P 500 has an APR of about 10%. So if you take all its ups and downs over its lifetime, it has averaged about a 10% gain per year. So suppose you invest an initial amount of $6,000 in the S&P 500 at 18 years old. How much money is in the account when you reach age 60? Assume a quarterly compounding. Well, the formula was A of t equals P naught times 1 plus R over N to the N times T. This is our model. Well, we know that we're starting with $6,000. The rate is 0.10. It's compounding quarterly, so that's 4 times per year. So if we actually do this out, we get 6,000 times 1.025 raised to the 4t. Right, so after we hit 60, we want A of 60 minus 18, right? We want how many years it's invested. Well, that is 42. So we have 6,000 times 1.025 to the 4 times 42, which is, what, 168? And this will give you about $379,980. Now, this is assuming that you don't add anything to the investment. So you just put the $6,000 in, you just let it sit and grow, and you don't add to the account. Then you'll have $379,980. The problem of adding money into the account as well is a problem that is tackled with calculus. You need the idea of an integral to tackle that kind of problem. So for now, this is the only kind of problem that we can examine. Now, if we consider the compounding interest problem, but let the number of compound periods per year increase without bound, that is, let n go to infinity, then we get what's called the continuous compounding formula, which is a of t equals p e to the rt. Now, note that when you are doing calculations with e, do not use the approximation. You will use the e key on your calculator. And I will show you how to do this in a tutorial video, which should appear right after this video. So, same example as last time, except now we're going to assume a continuous compounding. So in this case, our model is now a of t equals p e to the rt. So it's 6,000 e to the 0.10 t. So we want a of 60 minus 18, which was a of 42. So this gives us 6,000 e to the 0.10 times 42, which is 4.2. And this will give us approximately $400,118. Now, when doing something mutual fund, it is more realistic to use a continuous compound to calculate how much money you're going to have approximately, because the amount that the stocks are worth increases and decreases consistently throughout the day. So that concludes our look at exponential functions. As I said, the next video after this one in the list should be a tutorial video, but then after that we will look at the logarithmic function.